In this lecture video, we're going to look at how to perform a left-tailed test about a population median. Now, let's suppose that we wish to perform an hypothesis test of the following form, where the null hypothesis says that the median of the population is greater than or equal to some specified value, against the alternative hypothesis, which says that the median is less than that specified value, and that we want to perform the test at a significance level of alpha. Now, let me just stop right here and talk about this significance level that we're wanting to use. As we've seen in the previous setup and the previous examples, it may not be possible to have a significance level of exactly equal to a particular value. That follows from the discreteness of the sampling distribution of the test statistic. So, for example, it may not be possible to have an exactly 0.05 level of significance. And so rather than say that we want a particular or specific level of significance, we might want to change that language a little bit and just say something like a significance level of approximately alpha. Or if we wanted to be a bit more specific and to be kind of conservative about it, we could say at a significance level of no greater than alpha. So we're going to think about that as we go on through these other types of hypothesis tests throughout the rest of the course, because that's going to be characteristic of all these tests because of the discreteness of the sampling distributions. Okay, so getting back to the hypotheses, the alternative says that the median of the population is less than this specified value. And so in other words, is there sufficient evidence to conclude the population median is less than this specified value M0. So if the goal of the research is to try to show that the median of a population is less than a particular amount, remember that we always put what we want to try to show, what we want to try to prove, in the alternative. And so this is how we would set these hypotheses up. And again, the hypotheses are logical complements of each other. And so if the alternative is that the population median is strictly less than cap M sub 0, then the opposite of that would be that cap M, the population median, is greater than or equal to that value. So this is how we set the hypotheses up. And then when we look at the sampling distribution under the null hypothesis, what we do is we look at the boundary conditions. So we would look at that equality portion. But specifying the hypotheses completely, this is how we would do it for a left-tailed test. Okay, so we'll need a test statistic in order to test this hypothesis. Can we use the same test statistic, EXST, that we used in the previous hypothesis test? Remember that the previous hypothesis test that we covered was a right-tailed test. All right? And so the question is, do we need to come up with a completely different test statistic, or can we utilize the same test statistic? Well, if EXST exhibits different behavior under the conditions of the alternative hypothesis than it does under the conditions of the null hypothesis, and if the differences in behavior can be identified and characterized, then yes, we'll be able to use EXST in this context left-tailed test as well. And I see that I have a typo here. I'll go back and fix that. Okay, so with this in mind, the next slide looks at the behavior of EXST, this potential test statistic that we're considering using for this left-tailed test. Now remember what EXST is, what it's measuring, okay, what it's equal to. EXST is the number of the y's that are greater than M sub 0, the specified value of the population median. On the next slide, we're going to look at the behavior of this potential test statistic, both under the null and the alternative hypotheses. Okay, so the graphic here on the right shows two distributions, one with median equal to cap M sub 0, and the other with median strictly less than cap M sub 0. So the green curve in this case corresponds to a distribution that we may be sampling from, the median of which is the hypothesized value of the population median. So M sub 0, but that's where this is centered. And again, as we did in the previous situation in the right-tailed test and in the development of that test, again here I'm using normal curves, primarily because that's what we're familiar with. I want to try to dovetail this new material with the material that we already know and are comfortable with. There's nothing about this development that actually requires the population that we're sampling from to be normally distributed. and I'll say more about that as we go on. Okay, but again, I'm just using, I had to come up with some distribution for this illustration, and I'm just using something that's fairly easy to create and something that we're familiar with. Okay, so having said that, we've got two curves here. Again, what are we trying to do here? We're trying to understand the behavior of X tote through its sampling distribution under the null hypothesis and under the alternative hypothesis. So I've got two example curves here, PDFs, distribution curves. One that is centered at the hypothesized value of the population median, cap m sub 0, and the other one that is consistent with the alternative hypothesis, cap m, the population median being something less than the hypothesized value. Okay, so remember that X tote is counting the number of observations that are strictly greater than m sub 0. So we're counting the number of Y observations that are to the right on the number line here of this point. Now, if the boundary condition of the null hypothesis is true, in other words, if the population median is equal to cap m sub 0, then we see that the probability of an observation being greater than cap m sub 0 is 0.5, because that's the area under this green curve to the right of cap m sub 0. On the other hand, if the alternative is true, so that the median of the population is less than or to the left of the hypothesized value cap m sub 0, so if the distribution that we're sampling from is centered here, then what is the probability that a particular observation from this distribution, from the red curve, is greater than or to the right here of cap m sub 0? Well, that probability is given by the area under the red curve to the right of that point, and we see that's something less than 0.5. So we see that whenever cap m is to the left of cap m sub 0, the probability of a particular observation being greater than cap m sub 0 is going to be less than 0.5. And so that's what we're saying here. If the alternative hypothesis is true, then this probability p is less than 0.5. And we can go further and say, and this illustration shows this, that the smaller m is, the smaller the population median is, the farther left that point moves, then the smaller the value of this probability. And so what values would we expect to see our test statistic X tote take on if the boundary condition of the null hypothesis is true? In other words, if the population median is exactly equal to cap m sub 0. Well, as we can see in this graph here, which by the way, this is the PMF of the distribution of X tote if the boundary condition is true and if n is equal to 10. All right, so this is the sampling distribution of X tote in that situation. And so as can be seen in this graph, the probability that X tote will take on a value greater than or equal to, say, 2 is given by the sum of these probabilities, and that probability is 0.989. So it's almost assured that if the null hypothesis is true, and in particular, if the boundary condition is true, that it's almost assured that we're going to observe a value of X tote greater than or equal to 2. And in fact, let's think about this null hypothesis. If the population median is actually greater than cap m sub 0, then this probability, the probability that X tote takes on a value greater than or equal to 2, is going to be even greater than 0.989. So if the null hypothesis is true, what we can say is that the probability that X tote takes on a value greater than or equal to 2 is at least 0.989. And so if the null hypothesis is true, it would be very, very unlikely to observe a value of X tote either 1 or 0. In fact, that probability is at most 0.011. So from this, we can conclude that if the alternative hypothesis is true, the random variable X tote will tend to be smaller than it is when the null hypothesis is true. Therefore, small values of X tote provide evidence against the null hypothesis and in favor of the alternative hypothesis. Now, we again make use of the fact that if the null hypothesis is true, and specifically at the boundary condition cap m being equal to the specified value cap m sub 0, then X tote has a binomial distribution with n trials and success probability 0.5. And so for this left-tailed test, the p-value is equal to the probability that x tote is less than or equal to the observed value of x tote, little x tote here, given or under the assumption that the boundary condition of the null hypothesis is true. And this probability is given by this sum, k going from 0 up to x tote, little x tote, of the PMF of this binomial distribution. And so we see here how we would calculate this. Once we have the p-value, then if the p-value is less than or equal to a particular significance level that we're using, then we would reject the null hypothesis. Now we can express the p-value calculation in terms of the CDF of x tote. And so, for example, let's suppose that we are doing this type of analysis, this left-tailed test, on a sample of size 10, and that the observed value of x tote is equal to 2. And so in that case, the p-value would be equal to this sum. And again, the formula I'm using is this formula right here. And we see that we have three values to add up, corresponding to k equal to 0, k equal to 1, and k equal to 2. So 10 choose 0 times 0.5 raised to the 10th power, 10 choose 1 times 0.5 raised to the 10th power, plus 10 choose 2 times 0.5 raised to the 10th power. And that turns out to be 0.0546875. All right, now we can very easily calculate this p-value. We can very easily evaluate the CDF of the binomial distribution using the TI-84 calculator. And again, you can also calculate this on a calculator like the TI-36X Pro and various Casio calculators as well. And we do this on the 84 and on the 36X Pro by evaluating the binomial CDF function, obtained from the distribution menu. And so you can see here in the upper rightmost panel that I'm selecting the binomial CDF function, and then I'm entering the particular values in the bottom right panel. So 10 trials, success probability of 0.5, and then we want to evaluate this at the observed value x tote equal to 2. And then when we select paste, it pastes it onto the calculator screen. We press enter and we get 0.0546875, which again is the same value that we calculated on the previous slide. Okay, so let's look at an example. So the data in the table below are a random sample from a normal distribution with unknown mean and unknown variance. Now again, just let me say, this procedure that we're using does not in any way, shape, or form depend on the normality of the population from which we're sampling. There are some reasons why I'm doing this that we'll see subsequently. I want to re-look at this data using some previous tools for comparative purposes, but again, the procedures that we're looking at do not depend on normality. We're going to again frame the question in terms of the population median and use this procedure that we just looked at to analyze the data. So the question is there sufficient evidence at the 0.05 level of significance, or we should probably say something close to 0.05, or perhaps we might want to use a significance level that is no more than 0.05. So the closest attainable significance level that is no more than 0.05. We could do it either way. So is there sufficient evidence to conclude that the median of the distribution is less than 75? So you just take a look at these data. What do you think? Is there sufficient evidence to conclude that the median of the distribution is strictly less than 75? So we see some values that are greater than 75. We see some that are less. And so it's going to be difficult to tell just by looking at the data. We actually need to run through the test. So the null and alternative hypotheses are set up as follows. What we're trying to show is that the median of the population is less than 75. And so this goes in the alternative hypothesis. The opposite of that, m being greater than or equal to 75, therefore goes in the null. All right, so this is how we set up the hypotheses. Now again, the rejection criteria can be specified either in terms of a critical point or in terms of the p-value. To specify the rejection criteria in terms of a critical point, remember that for this test, we will be rejecting the null hypothesis for small values of x tote. because small values of X-tote are consistent with the alternative hypothesis. How small does X-tote have to be in order for us to reject the null hypothesis and conclude that the median of the population is less than 75? Well, to answer that, we need to construct the sampling distribution of X-tote under the boundary conditions of the null hypothesis. Under the boundary conditions of the null hypothesis, the test statistic X-tote has a binomial distribution with n equal to 18 and success probability of 0.5. So we have a sample size of 18 observations, so that is our n, that's the number of trials in this binomial distribution framework. And the next slide then shows the necessary information about this sampling distribution. So in the first instruction here, I'm constructing the sample space, the integers from 0 to 18. So those values go into list 1. And then in the next instruction, I'm calculating the values of the binomial CDF for each of the values in list 1. So the CDF values go into list 2. Now remember that we're going to be rejecting for small values of our test statistic X-tote. And so we can see here that we don't see 0.05 exactly in this second column, this second list. But we do see something very close to it and a little bit less, so 0.0481. And so we could choose to use more specifically a significance level of 0.0481. And again, because column 2 contains the values of the CDF, that 0.0481 corresponds to the probability of observing a value of the test statistic X-tote less than or equal to 5 if the boundary condition of the null hypothesis is true. Okay, so we've got our hypotheses, and now we can come up with our rejection criteria. Having looked at the sampling distribution of the test statistic under the conditions of the null hypothesis, right, we can come up with our rejection criteria. Now, again, restating what I said on the previous slide, note that there is no value C, we'll call it C, there's no value, this is the critical point, there's no value C for which the probability that X-tote is strictly less than C, given that the boundary condition of the null hypothesis is true, that is exactly equal to 0.05. The CDF probability closest to 0.05 that does not exceed it is 0.0481, which we identified. And the corresponding value of C is actually, this should not be 5, this should be 6, shouldn't it? Because we're talking about strictly less than. So let me go back to the previous slide and just confirm. Oh yeah, okay, so I see here. So this is the probability that X is less than or equal to 5. If we want to express it in terms of values that are strictly less than, this probability to be strictly less than a number, it would be 6. And it's actually much more informative to express the significance level being used in terms of the attainable significance level, because you're actually, if we were to say 0.05 here and not express it in terms of the actual attainable significance level of 0.0481, then we would not be informing the readers of the research that the results we have are actually stronger than they are if we just say 0.05 as our significance level. Because remember, if you use a smaller significance level, then you're requiring more evidence against the null hypothesis in order to reject it. And so by saying that the significance level that we're using is actually the attainable value of 0.0481, we're actually providing information that the test is actually requiring more evidence against the null hypothesis than it would be if we were using a significance level of 0.05. Okay, so we calculate the value of the test statistic. Okay, now remember again what X-tote is measuring. It's counting the number of observations that are greater than, in this case, 75, and there are only 6. For this left-tailed test, the p-value is the probability that X-tote is less than or equal to this observed value under the conditions of the null hypothesis. This is just the value of the CDF for X-tote when the binomial probability is 0.5. And so I've got that evaluated here in the panel on the right. And so we see that our p-value for the test is 0.1189. We can state our conclusions, and we're going to state them, illustrating how to state them using both the test statistic and critical point method as well as the p-value method. So I'm doing this for the sake of completeness. In a real-world situation, you would not use both methods. You wouldn't use the test statistics / critical point method and the p-value method. You would use one or the other, and you would probably, more than likely, use the p-value method. For completeness and for teaching purposes, I'm showing how to do both. So remember that we said that we were going to reject the null hypothesis if x tot was strictly less than 6, right? And since that's not the case, there is insufficient evidence at the, and now I'm saying, so here a 0.05 level of significance to reject the null hypothesis and conclude that the median of the distribution is less than 75. Now, when we are failing to reject, it's actually okay to use this 0.05 level of significance instead of the 0.0481, because remember, when you use a larger level of significance, you're actually making it easier to reject the null hypothesis. You're requiring less evidence against the null hypothesis, and you're giving your test more power than you would if you were using the lower level. So by reporting it this way, we're actually showing that the test would not be rejected even at this larger level. Now we can also state this in terms of the p-value, and so based on the p-value, which was 0.11894, since that is not less than the significance level we're using, then we would fail to reject the null hypothesis. And one of the advantages, again, of using the p-value is that you get more information about the strength of the evidence against the null hypothesis. And so we can see here that based on the p-value of 0.11894, we see that we would fail to reject the null hypothesis not only at the 0.05 level, but also at the much higher level of 0.1. In fact, any significance level that is less than 0.11894, we would fail to reject the null hypothesis. Okay, so that wraps up a particular lecture video on performing a left-tailed test about a population median. In the next video, we're going to look and see how to perform a two-tailed test for a population median. So I'll see you in the next video.